Hello once again. This is Bruce Wallenberg. This is lecture 15A, titled Interchange, Pooling, Brokers, and Auctions. This is the first of 2 lectures on this topic. The question we're going to deal with at the beginning is, why do electric companies interconnect and interchange power with neighboring systems? Many power companies, when they started, were isolated. They might have been serving one industry or one mine, for example, or one city. But eventually they built up enough of a network that they could run higher voltage transmission to another city, to another power company, and then to another. And pretty soon they were networked. And now virtually in the United States, networked completely across North America. And that's true for most of the developed world. But why do it? Number one, it's better to buy power from your neighbor. So you buy power from your neighbor if your neighbor can generate the power cheaper. That's the simplest and easiest explanation right there. If you have a neighbor that can generate the power cheaper than you, and they have enough fuel, or they have, let's say, hydro, and they have spare capacity, and they're willing to sell, well, and they're willing to sell cheaper than you can do it, turn your generator off and buy it from them. It has the advantage that if you're both operating and one of you has a generator failure, for example, then the other one can bring their generation up, keep everybody's lights on until you get your situation changed, until you straighten out. So there's a reliability as well as an economic reason. Lastly, it's easier to control frequency if you're in a large interconnection. If you have a large load change or a large generator goes offline, then there are hundreds of generators. They all can take a little bit of governor action and keep the frequency where it should be, much easier than if you just have a few generators. So we're going to review the following topics: interchange categories. There's just many of them. Energy, dynamic energy, contingent, market, transmission line use, and reliability. We've touched on these couple of these topics already. So under energy transactions, we have what is called economy A, and that's simply, and we'll show you some examples with numbers later, but it's simply a matter of, I talk to my neighbor, his cost is let's say lower than mine, so we split the difference in the cost, and we agree to transfer so many megawatts. And the idea of bringing both of us bring our incremental costs equal to each other. Economy B is the same thing, whereby I might look further out in time and I might commit a unit in order to sell power to my neighbor because they need it and they're willing to pay. And so the difference between economy A and economy B is simply that in B, we're willing to consider and actually commit generating units or decommit, whichever, in order to set up the transaction. Unit sales. Suppose I bought and helped pay for a portion of a large generating unit, but it sat within my neighbor's system. Then I'm basically importing power from something that I own, or I've just bought a portion. Let's say I bought 20% of its output. So now I'm buying. That's, instead of building a generator, I can buy a portion of my neighbor's generator. They call it unit sales. Diversity sales happen whenever systems have different peaks. This may happen across a time zone line, for example. If my system peaks but a different hour of the day, my neighbor's system peaks, well, when his is peaking, I can sell power to him, and then when mine is peaking, he can sell the power back. So the diversity, just peak, it depends on when the power systems peak. Again, more energy transactions, energy banking. If I have a large neighbor that needs power, I during certain times of the year I may just sell power to them, but we won't price it. I'll just say I'm going to sell you so many megawatt hours, and then later on, however we work that out, they're going to sell back the same megawatt hours, but we're not going to price it. We're not going to try to account for that, and that's a very handy way of selling energy, or sort of depositing energy. You got to have a willing neighbor to do that, of course. Inadvertent says that I've done some interchanging with the neighbors because my control system for my generators or my AGC wasn't doing the correct thing, and I have transferred too much power, or I've had too much power come into my system than I scheduled for. That's called inadvertent, and there's an arrangement whereby we set up a transaction to pay back that inadvertent, and also to sort of true up all of the schedules. Take or pay, like the gas contracts, you can have an interchange contract where the neighbor says, okay, I've got so much here for this price and you buy it, but if you don't take it, it's a take or pay. If you don't take it, then you lose the money, but the neighbor doesn't have to suffer. He gets his money. Dynamic energy transactions. This is where the power is going back and forth. If we have a jointly owned unit, so here's a case where there's a unit, let's say in my area, but it's let's say half owned by my system and half owned by his system. Well, then a jointly owned power plant, who controls it? Well, we literally set up an interchange schedule that can be freely moving up and down, so that as my neighbor's load changes, the neighbor can send changes to the output to help control the frequency in the system, but basically it's controlling for the effects in his own system. So in that case, the interchange is moving up and down all the time, and it's not scheduled in that respect. Remote demand, a load can be I can say, okay, I have a load in another control area. Let's say it's a large industry, and they're buying power from me. And so as that control area comes up, they transfer the command signal to my AGC, and the power just automatically flows to that load without setting up an actual formal schedule of interchange. Contingent transactions, there's lots of contingent ones. We talked about this is the reliability area. Another system can help cover your generation. If I have to carry so much capacity reserve, in other words, I've got to have so many generators online at a certain capacity. Well, if I don't have that available, then I can buy some capacity from the neighbor. Now that says that I don't actually go get it until I have an emergency. So there's a contingent there. Emergency, of course, is when I lose a large generator and I have an agreement with my neighbor that basically says, hey, the frequency just starts going down. He helps his governors come up, and he helps them initially, and then we go into an emergency transaction until I can get the generation back up, or I can get another generator started. But it's an agreement to do that for a certain price. Spinning reserve is another system, can help cover your spinning reserve. Ready reserves, another system, can help you cover forced outages with generation that's ready to start up. So ready reserve is not the same as spinning. Spinning, of course, it's synchronized and I can bring the generator up quickly. Ready means I've got to start the plant. It may start quickly if it's hydro or combustion turbine, or it may take many hours, but I can buy those reserves as well as spinning reserve from my neighbor. Market-based transactions. Some examples that we're going to talk about: demand-side management, meaning I can manage the load. I can turn the loads on and off. the Florida energy broker, and we're going to talk about markets such as the PJM, New York ISO, Midwest ISO, New England ISO, etc. Here. These are just in the United States. Now, if you're going to use somebody's transmission, pardon me, if you're going to use somebody's transmission, suppose I'm going to send power from my company to a neighbor's company, but some of the power is going to flow through other companies. How do I reimburse the other companies for the use of their transmission? And there are several ways of doing this transmission cost. The simplest is just called postage stamp. You average costs over all the transactions over a long period of time, and then there's a flat rate, and that's like sending a letter. It doesn't matter how far the letter goes. I can send a letter to the house next door. I can send a letter all the way across the country for the same postage stamp, up to a certain size or weight. If you want to be more accurate about it, you can use what's called dollar per megawatt mile. Each transmission line is assigned a cost per mile, and then each transaction must be assigned how much of the transaction goes on each line. You multiply that times the dollar per mile cost times the megawatts, and you come up with a dollar amount that tells you how much that transaction is to be charged. Transmission use transactions. A typical example, again, we talked about it before, is jointly owned. We talked about jointly owned units. Here we're talking about jointly owned transmission. You might build a large transmission line with your neighbor, each paying part of it, and so then there's got to be some requirement over control of the flows to reflect that contract. You don't want each to own half the line, but most of the time your neighbor's using 90% of it, for example. There's got to be an arrangement so that we control the flows. We can each use it. Okay, locational marginal pricing to cost transmission use. If I want to transmit P sub W amount from bus I to bus J, I go at bus I and I sell PW to the system at the LMP there. So I'm basically selling it into the system, and I get paid the LMP at that bus I. Then I withdraw PW from another bus J, and I have to pay the LMPJ. Now the cost of the transaction then is the difference in the locational prices times the megawatt. Very common way of doing a transaction costing. Here's an example of that. We have here's the PW is 20 megawatts. It's going to go into bus 3, and we're going to take 20 megawatts out down here. We take our 6-bus system, so we're sending the transactions from here all the way down here, in at bus 3 and out at bus 4. Now, if I took the system with no transactions and no limits, these values here of LMP, they're the bus. These are the LMP values here. We call them lambda P. L, locational marginal price. These are just due to transmission losses and some difference in the cost of generation and so forth. Now, when I do the 20 megawatt transaction from 3 to 4, no line limits checked. That's interesting. That's here. Then I've shown you that the total operating cost and the line flow from 2 to 4 is 77, but the limit that should be less than 60. So we've got a problem with one of the line flows. But we're going to look at the 3-4. We're going to look at these costs here, and we'll see that on the next page. So the unconstrained case here, 13.24 minus 12,376, that's the cost, that's the difference in marginal price. If I put the transmission line on limit, then I get some very different prices between 3 and 4. And you can see down here it's 16.47 minus 12 or 4.2. It jumps by quite a bit to get the cost difference. So that method it means it's going to cost you if you're sending some power and you're causing some congestion on the system. You're going to pay a lot for the transmission service. Here's another example of economy interchange. We have two areas like this with each one has 3 buses. Wow, they have more than 3 buses, 3 generators. And we have composite curves for 1 and for 2. And here's the ABC coefficients, and the first one goes 300 to 1200. This one goes 360 to 1470. And the load in the first area is 700. The load here in the second area is 1100. That's 1800 megawatts. If we just serve the 700 in area 1, we're paying an incremental cost of 20 here. If we're selling the 1100, we're paying 2400 at the second area. And then we totaled up the total operating. So the total operating cost for both areas is $36,326. Now, I'm going to do some interchange to approximately bring these two costs equal to each other. And so I'm going to the load here, I'm going to change the load and change the load here, and I'm going to interchange 286 megawatts from area 1 to area 2, and now the total operating cost drops by quite a bit. So we've equalized the incremental cost, and I brought the total savings. I brought some savings down. So the area 1's cost increased, area 2's cost decreased, so there's a savings. Okay, I had to bring the generation up in area 1, and I had to reduce it in area 2. So the amount of reduction is greater than what he increased, so there's a savings, and what they would do is simply split that number across each area. Now, each area runs an economic dispatch of its own. The system with the lower incremental cost runs a series of calculation with increased load. The system with the higher incremental cost runs series with decreased load. Now what you're trying to do is you're trying to see where they're going to cross over. So it's like this, and you have one area, this is incremental cost, and there's one area is higher than the other. So he starts decreasing load, and it'll start bringing his cost down. He starts increasing. Wherever they cross, that's the incremental cost, and that tells you where each area should operate. Evaluating economy energy with unit commitment. It's very similar, except in this case, as we add load to one area, drop it off the other, we may have to take units on, put more online, or take units off, and look at the incremental cost the same way. So it's similar to the economy, but we're allowing generating units to go on and off. This is an example of wheeling. I'm going to send 100 megawatts. All I want to do is to send 100 megawatts from this area to this area. But look at what happens. 50 of it goes here, 50 of it comes down here, splits into 25, then 50 comes up here, and 50. So the 100 megawatts gets there. Okay, we do deliver 100. But meanwhile, all of these systems over here, this one, I'm kind of coloring them in. All of those are being used by this transaction. That's an example of wheeling and what we call the problem of parallel paths. Okay, power pool. The idea of a power pool comes up as follows. We have many different companies, let's say in a large state, and we would like to maximize the economic benefits of interchanging power for all of them. But each one trying to call, let's say there's 5 of them, so each one has to call 4 others. It gets much too complicated to set up transactions one at a time between each company and its neighbors. So what we do is as follows. We can minimize the operating costs. We could even perform a system-wide unit commitment. We can minimize reserves. We can coordinate maintenance scheduling, and we can maximize the benefits. And we do this because everybody says, okay, we're going to set up some sort of central office. We're going to tell the central office what our costs are, what our load is, and let the central office dispatch and do the unit commitments and maintenance schedules, etc., as if everybody was in one company. As if everybody was in one company. And that ends up giving us a much cheaper overall cost for all of them together. Now, there are some disadvantages. There's a complexity to the structure. You've got to have a lot of personnel and to administer the pool. There's operating and investment costs associated with the office. There's got to be lots of communications, equipment, computers, buildings, backup power, etc., offices, and so on. You relinquish the right to engage in independent transactions. Now, some companies may not like that, but the pool, they have to weigh that against what the pool savings would be for them. There's additional complexity that might come up with dealing with regulatory agencies. Okay. If the pool operates in more than one state, that regulatory agency thing gets to be very, very tricky. The feeling on the part of management of some utilities that pool structure is displacing some of the individual systems management responsibilities. Well, this may get to be a problem that they want to do certain things and the pool says no. Then there's a conflict, and they have to work that out. Some of the freedom of independent action that's possible. If they want to take advantage of an opportunity, they can't. It's got to be done by the pool. The problem of economic allocation in the pool. So we all put all of our information into the pool, and it dispatches the whole thing. Well, now, how do we reconcile all this at the end? How do we go back and say who gets what? So who will pay what to whom for all of the economic transactions and special reimbursements and so forth? No pool member. This is sort of a dictum here. It says no pool member should have higher generating production expenses than it could achieve by dispatching its own to meet its own load. Obviously, if you joined the pool and it was costing you more, you wouldn't join. So that's pretty obvious, but it's something that has to be built into all the contracts and so forth. There's 2 types of ways of doing this. The first way is the pool acts as a purchaser. Everybody sells to the pool, and then they turn around and they purchase from the pool at the pool's rate. So if I'm a very high cost seller, I sell to the pool, and then the pool gives me the opportunity to buy back to supply my load at a lower rate. Similar, if I'm a low price, I get to do that too. In either case, you should be saving money. The other is that we run the whole power pool, and then each participant goes back and says, okay, what would it have been if I'd done my own, if I'd have supplied my own load? They call it own load dispatch. So I go back and I say, okay, if I did that, I would have run these generators against this load for these many hours and so forth. and that would have cost me so much. Now, we take all of the participants' own load costs and subtract the pool operating costs. Whatever the total pool operating cost was, should be lower. And the result is the savings, and they're allocated according to, you can do it by capacity or by megawatt hours or whatever is in the contract. So everybody comes in and says, this is what it would have cost me, add them all up, subtract the pool operating costs, and there's your savings. Thank you very much.